Okay, so in this lesson, we are discussing the integral and p-series tests. As you can see in this objective, determine whether a series of positive terms, specifically, converges or diverges by the integral and p-series tests. Definitely tests you should expect to see on your AP exam. So let's start off by looking at a couple of warm-up exercises. The first warm-up question, determine whether the series summation from n equals 1 to infinity of 1 over n converges or diverges. So let's take a look at what this series actually looks like. It's a pretty popular series here. So it is, if I stick in 1, I'd get 1. If I stick in 2, a half, stick in 3, I get a third, and so on, a fourth, a fifth. This is called the harmonic series. We'll see why it's called harmonic series in a bit, but we only have 2 tests so far. We've got the one for geometric series, which this is not geometric. There's not a common ratio here. And then we also have the nth test for divergence. That's what we're going to look at, right? So the nth test for divergence, it just looks at the nth term, not of the series, but of the sequence that we're adding up, and checks to make sure that the terms go to 0, right? So that's what we're going to do. We take the limit of those terms. If I were to plug in an infinity there, that'd be 1 over infinity. That's pretty much 0. What does that tell me? That tells me a whole bunch of nothing. It tells me nothing. So I don't have enough information. If your terms go to 0, maybe it converges and maybe it diverges. We don't know. All right, so this is the goal for, this is one of the goals for this particular lesson, is to try to resolve this question. Harmonic series, what's it do? Does it converge? Does it diverge? Right now, don't know. All right, here's the second warm-up question. Evaluate each of these improper integrals. So on the first one, we got the definite integral from 1 to infinity of 1 over x dx. And then we have over here on number 2, the same kind of thing except for the functions 1 over x squared. All right. Let's give these a try. And yeah, it looks like something that we've already done here before. You'll see what it has to do with the integral test and the p-series stuff in just a minute. So the first one is definite integral from 1 to infinity, 1 over x dx. It's improper. I know it's improper because, look, there's an infinity as one of the bounds. So remember, if this is a free response question, if it was, you need to absolutely turn that into a limit or you don't get credit. So it's the limit as b goes to infinity of 1 to b of 1 over x dx. All right, and now we can do the integral or the antiderivative part of it. Bring down our limit. The antiderivative of 1 over x, or dx over x, is the natural log of the absolute value of x, and then we'll evaluate that from 1 to b. And then using good old FTC, we're going to plug in our b. I'd have the natural log absolute value of b minus the natural log of 1, which of course is 0. Not that it really matters, because whenever I put in my infinity, this is going to shoot off to infinity slowly, but still infinity, which means this is equal to infinity and it diverges. The area gets infinitely big, so the area diverges for that particular integral. If we're talking about the area under the curve from 1 to I don't even know what, it gets infinitely big. All right, so let's look at the second one. Number 2, definite integral from 1 to infinity of 1 over x squared this time. Again, I need to turn it into a limit because I have an improper integral, b to infinity, 1 to b of, I'll rewrite that as x to the negative second power. So this time, of course, we'll use the power rule on it. Limit as b goes to infinity of, that would be x to the negative 1 power divided by negative 1 from 1 to b. Maybe, go ahead and rewrite that as negative 1 over x, evaluating that from 1 to b. FTC's coming in. B goes to infinity. That'd be negative 1 over b minus a negative, so plus 1 over 1 is 1. sticking in infinity here, that term's going to go to 0. I've got negative 1 over something getting super big. That'll go to 0 plus 1, whoops, is pretty much equal to 1, which means that this thing converges. Hey, pen, work. So the area, if we were talking about the area for this improper integral, converges to 1. Let's take a look at the graphs for those. So here's that first one. We have an infinite area for that graph underneath 1 over x from 1 to infinity. But this one, man, the graphs look so similar. But this 1 over x squared, it compresses down to that x-axis fast enough that we accumulate a finite area instead of an infinite area. And this was something that we had talked about when we did the improper integral lesson. And now specifically on this, the exponent on the x is a 1. And whenever it is in between 0 and 1, this thing is going to diverge. Anytime it's bigger than 1, it will converge, as we saw from those two examples. It has something to do with the integral test. All right, and the p-series. Okay, so here's the last warm-up question here. As if there haven't been enough, show that f of x is equal to e to the negative x is positive, continuous, and decreasing for x is greater than or equal to 1. Why am I doing that? As you're going to see, the reason why we're doing that is because these are the necessary conditions for the integral test. Your function has to be positive, it has to be continuous, and it has to be decreasing over some sort of interval. Usually it's greater than or equal to 1 in order for you to even consider the integral test. So let's check those things. As a matter of fact, 100% of that is all stuff that we did before we even learned how to do integrals. So for our third warm-up question, our equation, example, no, it's not example, it's warm-up. Warm-up 3. We have a function e to the negative x. I need to first consider whether or not it is positive. That's not how you spell that word. All right, I think I got it. So is it positive? Well, I mean, if you take a look at the graph, it is exponential. If you take a look at the graph, it's exponential, specifically exponential decay. And then here's the graph for that. It's always going to be positive. There's no exponent that you can raise e to get 0 or anything negative. So in this particular case, f of x equaling e to the negative x is greater than 0 for all x. So if it's greater than 0 everywhere, then definitely it's greater than 0 for x is greater than or equal to 1. So our first condition has been met, right? Our second one is the thing continuous? Is it continuous? Well, it's an exponential equation, and exponential functions are continuous everywhere. So yes, so f of x equals e to the negative x is exponential, which is continuous. We're continuous everywhere. And a lot of times, as far as the continuity goes, you just pretty much have to point out what kind of equation you've got or what kind of function you have. Oh, it's polynomial. Polynomials are continuous everywhere. Oh, it's a rational function. Well, rational functions are continuous on their domain. You just have to take out their asymptotes, and it's continuous everywhere else, right? So our second condition, check. Our last condition is decreasing. So condition number 3, decreasing? How do I tell whether or not a function is decreasing? I look at its derivative. I see if its derivative is positive or negative. So let's take its derivative. f prime of x should be equal to e to the negative x times the derivative of the interior, which is a -1. So it's negative e to the negative x. And remember, we just said that this whole thing is positive. Oh, wrong color blue. That is always greater than 0, so that one's always positive. And if that's always positive, and we just made it negative with the negative sign out front, no matter what, this thing is less than 0 for all x. All right, so we know that the first derivative is negative. If the first derivative is negative, that means our function must be decreasing. Since f prime of x is less than 0 for all x, all values of x if you wanted to say that, then f of x is decreasing. You know, I've turned on silent mode or whatever it is, do not disturb mode, and it does exactly nothing. Oh, I'm sorry, did you not want to be disturbed? But I have this super important thing to show you. Anyway, it's decreasing, and we needed it to be decreasing for x is greater than or equal to 1. I mean, it's decreasing everywhere, but surely it's decreasing there, right? Again, I wanted to be able to check these things very, very easily because, as we will see, those are going to be the necessary conditions by which we can use the integral test, which brings us to what our objective is. We're going to be able to, in this lesson, determine whether a series of positive terms, so I'm going to stop right there. That was one of the things that we had to check. Is our function positive? Okay. Whether it converges or diverges using this thing called the integral test or the p-series test. What you see here in the picture, these are vibrating strings, and you can recognize the numbers. You got 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. Those are the harmonic frequencies for which the harmonic series is named. All right, so when we come back, we're going to talk about specifically the integral test, how it works, what the conditions are supposed to be, and then maybe do an example or two.